full screen il കാണാൻ കഴിയുന്നുണ്ടോ?
Yes, sir. Now it is fine.
Is it moving?
Not now, sir.
Moving
Yeah,
in full screen?
now it is moving. Yeah, moving.
In full screen?
Yes, sir.
Okay, fine. Thank you very much, Ms. Nishida, for extending me an opportunity to interact with you through the lecture. Surface area and porosity determinations of porous materials for industrial applications. I am also thankful to the head of the department, the principal, the entire management of Muthoot Institute of Technology and Science for wonderfully organizing a 5-day faculty development program, Advanced Soil Reclamation Techniques. Actually, 1 year back, Nishida contacted me over the phone about the conducting of such a very important faculty development program, and some of the discussions have been made. I thought of that the program might have happened in the last year itself, and maybe due to the lockdown, it was conducted in a finest way by online. Just recently, again, the topic came to mind. A lot of discussion between your coordinator and me happened, and how we can integrate a topic related to physical chemistry and most prominently in analytical chemistry or analytical science that is very prominent at the interface of adsorption engineering and chemistry and physics of materials can be inducted in such a faculty development program where most of the engineers are the participants, especially of having chemical engineering and civil engineering background. I will tell you that the determination of surface area is very, very important in material science, in metallurgy, in nanomaterial science, in civil engineering, and wherever the materials are involved for the satisfaction of your passion of inquiry and research. This area is highly specialized, is a narrow analytical subject developed by some physicist. Of course, in those days, the physicist might be a chemist also. Even nowadays, we can see that most of the research in the field of physics and engineering is closely related to the applied chemistry aspects and analytical chemistry aspects. Without having any basic fundamental understanding of analytical science, especially analytical chemistry and the fundamental rules of chemistry and material science, nothing can be fruitfully done, even for an engineer. Because in CUSAT, many of the engineering faculties and research scholars working in civil engineering, they often come for discussion and they want to know what is pH, how the molar solutions can be prepared, what is ppm values, parts per million values, how the weight percentage can be calculated, how the solutions can be mixed. That kind of issues are arising everywhere. Also in the biological science, whenever a special analytical tool is applied for, especially for the E. coli analysis, Escherichia coli analysis or microbial analysis, large number of analytical reagents can be prepared and should be applied. The gathered data can be scientifically interpreted based upon the fundamental rules of physics and chemistry. So nobody can escape away from the practical application of analytical science. Here I am introducing you very important analytical science that developed basically as an applied knowledge followed by soil scientists. You know, in soil science, water continuously percolate into the different horizons of the soil. That water has the capacity to solute or to dissolve whatever the ingredients it interact on its way during the natural course of flow. It concentrate whatever the ionic components it is interacting and get dissolved. The ionic concentration is more. Even you analyze a sample of groundwater, enormous ionic compositions are there. Even the hardness is a very important parameter. The civil engineers are mostly depend upon when the construction material is discussed. The quality of water used for construction is very, very important because the hardness will be a very important factor. The salinity and the sodium content and the chloride content are very important when the concrete is mixed using a water, because water composition is very, very important because the water contains large number of ions. If that water is continuously moving through the soil, what is the effect of ions on the soil surfaces? How the ions are get trapped or get accumulated on the surface of the soil? So what is the energy that promote the interface mass transfer of ions with the solid matrix of the soil? Ultimately, the phenomena capillary rise and capillary condensation is interpreted in many ways by physicists and soil scientists. That means during the interface mass transfer, the molecules can be moved through the solid phase, mainly because of the surface area and the surface energy of the solid matrix. This vision, when a solvent is interacting with a solid surface, the porous structure is get filled with the molecules of solvent or the solution. The porous structure that is filled with the solvent, the ions can percolate through the soil to the liquid medium, into the liquid media, and ultimately, due to the mass transfer phenomena, the ions can accumulate and get concentrated on the surface of the solid surface. Here comes the significance of porosity of solid materials. Once the porosity is known, different types of porosity we have, the tapping porosity as well as the microporosity as well as mesoporosity and macroporosity of enormous number of materials used for industrial applications, especially cement materials, clay and ceramic materials, catalyst used for various applications, especially for the Haber synthesis for the ammonia, for the contact process, sulfuric acid manufacturing process, catalysts are widely used. In refinery, for the cracking and refining process, enormous number of catalysts are used. Everywhere, the activity of those materials are decided by the surface area of the material and the porosity of the material. That is the significance of introducing this lecture, surface area and porosity determinations of materials for industrial applications. Come to the second slide. The progenitors of this science, analytical model and mathematical relationship, and who interpreted the meaning of adsorption science to the entire scientific community. Of course, they were regarded as the most eminent scientists of the last century who contributed much for the economic engineering and development of the modern era, who were nobody other than Brunner, Emmett, and Teller. This name may be very familiar with chemists and somehow with the physicists, and in certain cases, in some cases, may be familiar with some chemical engineering professionals. So Brunner and Emmett and Teller, they were very established scientists of the United States of America. They developed a theory as well as an analytical instrumentation method for the determination of surface area, and that theoretical contribution is known as Brunner-Emmett Teller equations. The analytical instrumentation is known as BET, surface area analyzer, that is BET, Brunner-Emmett Teller surface area analyzer. Once upon a time, then publishing any standard research paper in an international journal, especially in material science, is a very, very painstaking issue of any of the research scholar working in Kerala. Because we don't have a surface area analyzer. Without a surface area analyzer, a porous material or catalyst material or any material, its activities depend upon the porosity can be characterized using a Brunner Emmett Teller analyzer. Nowadays, we have this instrumental facilities in many of the universities. Here, we know that when a solid material can absorb any gas as a function of relative pressure, a solid material, when it is subjected to adsorption by varying the relative pressure, the volume absorbed by the solid matrix can be a straight line. Here you can see a straight line relationship. Here in the y-axis, relative pressure is plotted. In the x-axis, in the x-axis, relative pressure is plotted. In the y-axis, the volume absorbed by unit mass of the solid material. That is, a solid material means a porous material having significant porosity and surface area can be applied, plotted on the y-axis. That conforms to a straight line according to Brunner-Emmett equation. That is, Brunner-Emmett equation is given here. 1 by volume of any gas adsorbed multiplied by relative pressure is equal to a constant minus 1 divided by the volume adsorbed, that is Vm, multiplied by a constant of proportionality and multiplied by P by P0 is equal to 1 by Vmc. This is a straight line equation that is perceived by Brunner, Emmett and Teller. This equation conforms to a straight line. This is a machine, I have mentioned that, but is a Brunner, Emmett, Teller surface area analyzer. This is a special vacuum-based analytical instrumentation. Here, any solid material of known mass can be folded on in the sample port, and it can be subjected to gas phase adsorption, changing the relative pressure. The amount of gas adsorbed with respect to relative pressure can be gathered from the instrument. That data is very, very important for plotting this graphical representative for the simulation of this graph. From this simulation of the graph, we can calculate the slope and intercept. This is the beauty and the scientific significance of this theory as well as the instrumentation technique. I will take you into a simple calculations because when we initiated our higher secondary studies in the +1 days, because now I know that you may be, most of you may be as assistant professor or associate professor, head of the department, maybe research scholars, but I am taking you the fundamentals of chemistry to the +1 level because anybody having a strong foundation in the +1 and +2, especially in the chemistry, physics and mathematics can only do some scientific critical thinking. Only out of the crucial critical scientific thinking, only new knowledge can be evolved out. That will be translated into publications and patent, and in the form of PhD thesis, the students can be trained as the research scholars. The science will be provided here even after the end of our lifetime. So let us go to some of the basic lessons of chemistry, and here I will show you the basic data gathered from a Brunner, Emmett, Teller equation, because the volume adsorbed is plotted against the y-axis in the y-axis, and the relative pressure is plotted in the x-axis, because the primary data generated from the instrument is known as an isotherm linear plot. This is the data we are generating from the instrument, because here, you know, quantity adsorbed, the quantity of any gas adsorbed on unit mass of porous material is plotted under STP in the y-axis. Relative pressure is plotted along the x-axis. So this is the graphical data we are generating from a Brunner, Emmett, Teller surface area analyzer. This data can be subjected to the calculations by Brunner, Emmett, Teller isotherm model. Then you will get a straight line graph. Initially, the instrument will give you a linear isotherm plot with the shape. The red line shows the adsorption and the reverse one shows the desorption. So adsorption desorption curves are obtained. Then when a porous material is subjected to interaction with any gas at a very low temperature, the pores are get preferentially filled by the gas molecules. When the pressure is released, whatever the molecules are loosely bound to the porous structure is released. That is the desorption. That desorption curve as well as the adsorption curve conforms to an isotherm linear plot. Isotherm linear plot means these curves are generated at a constant temperature. If the instrument is allowed to work on using liquid nitrogen gas, at 77 K, 77 K is equal to minus 196 degrees centigrade. That is a very low temperature we can easily maintain under laboratory condition, because minus 196 degrees centigrade is the easily maintainable lowest temperature anybody can have in our laboratory, because liquid nitrogen exists at minus 196 degrees centigrade. That is equal to 77 K. So if you want to conduct some experiment, you procure some liquid nitrogen, keep in a dewar flask, the specially designed dewar flask. This name is also very familiar to you from the pre-degree classes or the +2 classes. What is the functioning of a dewar flask? So the liquid nitrogen can be procured from industry and you can keep in a dewar flask. You can place the sample. You want to do some experiment into the liquid nitrogen, so the reaction temperature will be 77 K or minus 196 degrees centigrade. Therefore, this kind of experiment are done at a constant temperature conditions. Therefore, these experimental data are known as isotherm linear plots. This is the linear isotherm plot. Then this is the graphical data we are calculated to obtain the BT surface area. This is an example for how this instrument ultimately give you a graphical simulation regarding the surface area. Then other pertinent parameters of porous material, that is BJH, adsorption and desorption isotherm plot for the cumulative pore volume determinations. Then comes to the instrumental part. This is a huge instrument, but it requires a lot of preparations. This is the main instruments. Nowadays this instrument is manufactured and supplied with the highest precision by Micromeritics industry USA. And any instrument that is those people revolutionized the analytical instrumentation surface area in the entire world. We have that analytical instrument that is manufactured and supplied by Micromeritics. It is a 3-flex instrument. Here you can see 3 sample pots. So the quick analysis, most of the micro and mesoporous material can be analyzed under laboratory conditions in this instrument. This is a small view of the porosity surface area determining Micromeritics 3-flex instrument. This is for just introduction. What is a surface area analyzer? Then let us wait for program to so my laptop has a simple problem. Wait for the program to respond. Nishida, hello.
Yes, sir.
Just wait. The laptop just started some problem. I will wait because I clicked into the picture. quickly rather than the slide.
Right.
ATM അല്ലേ? അതുകൊണ്ട് എടുക്കണ്ടേ? അത് ക്ലോസ് ചെയ്ത് പോയോ? പിന്നെ ഇതെടുത്ത് ഇല്ല. അപ്പോൾ ഹാർഡ് ഡിസ്ക് ക്ലോസ് ആയിപ്പോ അല്ലേ?
അതെ സാറേ പോയ ഹാർഡ് ഡിസ്കിന്റെ ഇടയ്ക്ക് പോയപ്പോഴാണ് സാറിന്റെ പ്രവർത്തനം സ്റ്റെപ്പ് ആയത്.
ഹാർഡ് ഡിസ്ക് പോയത് പോന്നോ? ഹാർഡ് ഡിസ്ക് ഇവിടെ വന്നില്ലല്ലോ. അല്ലേ, ഈ സി ഗേറ്റ് എക്സ്പാൻഷൻ ടച്ച് ചെയ്തോന്നല്ലേ? കണ്ടെത്തുന്നുള്ളത് ഇത് അപ്ലൈ ചെയ്ത് 5-4 നോട്ട് 5-4 അടിച്ചു. പ്രസന്റേഷൻ 1 ഇപ്പോൾ വന്നിട്ടുണ്ടോ? അനങ്ങി പോയതായിരിക്കും അല്ലേ? അറിയില്ല. വലിയ സ്ക്രീനാക്കി ലാപ്പിലുണ്ട്. അപ്പൊ മെമ്മറി കൂടുതൽ എടുക്കാതിരിക്കാൻ വേണ്ടി ഹാർഡ് ഡിസ്ക് എടുത്തത്. അത് പിന്നെ മാറ്റാം. കാണാമോ? ഹലോ,
Yes, sir. Yes.
ഓക്കെ. സ്റ്റെപ്പായോ? വീണ്ടും സ്റ്റെക്കായി അല്ലേ? അപ്പൊ ഇത് മറ്റേ ഇത് മാറ്റിയിട്ട് അതിൽ നിന്നെടുത്താൽ മതിയല്ലേ? ലാപ്പ് എടുത്ത് കണക്ട് ചെയ്തോ പാരലായിട്ട് കേട്ടോ. ഇതിനെടുത്താൽ മതിയോ? അത് കഴിഞ്ഞിട്ട് ഇത് കഴിഞ്ഞിട്ട് അവിടെ വരുമ്പോൾ പ്രോബ്ലം ആയത് വീഡിയോ ആണോ അത് വീഡിയോ ഓൺ ചെയ്ത് അത് വീഡിയോ ആണോ അതായിരിക്കും അത് ഒന്നല്ലേ വീഡിയോ സ്റ്റക്ക് ആയതാണോ വീണ്ടും സ്റ്റക്ക് ആയല്ലേ
സിസ്റ്റത്തിൽ ഫോൾഡർ ചെയ്തെന്ന് അറിയാം.
ഉണ്ട് സിസ്റ്റത്തില് ഇതിന് വരുന്ന പ്രോബ്ലം ആണോ
മാറ്റിയെടുത്ത്
അത് മാറ്റിക്കും സിസ്റ്റത്തിൽ എപ്പോഴത്തെ ഇതും കൂടെ കിടക്കണം ഇത് ക്ലോസ് ചെയ്തപ്പോൾ ഇവിടുന്ന് റിജക്ട് ചെയ്യണ്ടേ ശരിയായ മറ്റിടത്ത് എത്തിക്കുന്നു അത് തൊടാതിരിക്കുന്നുണ്ടല്ലേ 5-4 അടിച്ചാൽ മൂവ് ചെയ്യുന്നില്ലല്ലേ അല്ല സ്കിപ്പ് ചെയ്യാൻ എങ്ങനെ പറ്റും വീണ്ടും സ്റ്റക്ക് ആയല്ലേ എന്നറിയാം മറ്റേ ഇതിലാക്കിയിട്ട് പിന്നെ അത് ഞാൻ അടുത്തെടുത്താൽ മതി മാറ്റിയിട്ടേ നെറ്റുണ്ടോ നെറ്റോടൊക്കെ ലിങ്ക് എൻ്റെ മെയിലുണ്ട് മെയിലിൽ നിന്ന് മനസ്സിലായത് കഴിഞ്ഞിട്ട് വാങ്ങിച്ചത് ഇത് കഴിഞ്ഞിട്ട് Nishida. Hello, Nishida.
Yes, sir.
Is it visible now?
Yes.
In full screen?
Yeah, full screen, sir.
Okay.
Everything is fine, sir.
Extremely sorry that my computer hanged a little bit, but my students interfered and they cleared the technical problem. Otherwise, if it repeats, another laptop is also getting ready, we can switch on to the next one. Here, this is the IUPAC technical report, because just like BAS or WHO, whenever a porous material has to be tested and characterized, this is the technical literature that explain what is a porous material. So anybody want to do something in future regarding the porosity and surface area determinations, this is the latest technical report that is published in 2015 by a IUPAC technical committee, that is physisorption of gases, with a special reference to the evaluation of surface area and pore size distribution by IUPAC technical report, because the analytical method or the methodology followed for the determination of surface area and porosity is the physisorption of gases. I have mentioned that a gas is allowed to interact with a porous material at a very low temperature, so that with respect to the applied pressure that is calculated in terms of the relative pressure P by P0, the volume adsorbed, the reduced volume adsorbed on the specific weight of the material is plotted as a graphical simulation. That graph is known as a normal adsorption isotherm plot. When the data is subjected to other calculations and it is subjected to linearization according to Brunner-Emmett equation, then you will get a straight line, and the straight line has a slope value as well as an intercept. From the slope and intercept, we can determine the surface area and porosity of the material. Because the scientists involved in the preparation of this technical report, especially Kaneko, and the last scientist, his name is Kenneth S.W. Singh. We refer him as KSW Singh from the Brunel University, UK. And another scientist is Marsh. I met Marsh in 15 years ago in a conference in the UK. And Francisco Rodriguez Reynoso, he is a very, very pioneering scientist in the field of carbon science, activated carbon science. He established a kingdom in the chemistry of porous materials by Francisco Rodriguez Reynoso. Of course, I met Katsumi Kaneko also. He's from a Japanese scientist. He made a lot of permutation on the BET isotherm, found that BET isotherm can be extendable up to the relative pressure P by P0 is equal to 0.35. That is a very significant contribution of Kaneko. Brunner and Emmett assumed that if you take a porous material, when you apply a relative pressure starting from 0.05 to 0.3, the most of the porosity will be saturated, and the linearity is maintained up to relative pressure of 0.3. This is the invention and the technical significance placed by Brunner and Emmett through a series of analysis. But Kaneko analyzed those data and later found that the BET equation is valid more than P by P0 is equal to 0.3. Up to 0.35, most of the porous material maintains BET, the validity of the BET equation. Then why porous material nature? You know, in a porous material or activated carbon or a soil grain or any powder material is taken, when it is analyzed under a microscope, just like our heart pumping our blood through veins and ultimately to the capillaries, here we can see a series of network on the porous material. So the channels having the width greater than 50 nanometer are regarded as macropores, that is the macropores having the width greater than 50 nanometer, and that is tapered into a narrow channels. Those narrow channels are known as mesopores, having the width between 2 to 50 nanometer. Those materials are known as mesoporous materials. The materials that are significant with the macropores are known as macroporous materials. The materials having the size less than mesoporous dimension, that is having the size less than 2 nanometers, are known as microporous materials. So the entire world is consisting of different materials, but based upon their porosity, they belongs to major three classes of materials: microporous, mesoporous, and macroporous materials. Of course, nowadays new term is there, that is a nanoporous material, not nanomaterials. Nanomaterial is entirely different from nanoporous materials. Nanomaterials having the size, any material having the size between 2 to 100 nanometer in size is known as crystalline size is known as, that is a crystal lattice is very important for nanomaterials. But in the case of nanoporous materials, any porous material having the size less than 2, less than 0.5 or 0.7 nanomaterials are known as nanoporous material. That is a graphical representation of pore structure in porous material. Here, activated carbon is taken as an ideal porous material. Why granular materials in nature? എന്തുകൊണ്ടാണ് നേച്ചറിലെ ഗ്രാനുലർ മെറ്റീരിയൽ ഉണ്ടായിരിക്കുന്നത്? നമുക്ക് സിമ്പിൾ ആയിട്ട് we can go to the example. Why grains are granular? You know, most of the grains, whatever the material you see in and around, are granular in nature. Especially the grain. Most grains are granular. Why? Because granules are a part of our heritage. You know, why grains? Grains are the they are the storehouse of energy for the entire ecosystems. For the animal kingdom, the main storehouse of energy for their livelihood are grains, because the granular structure, that is a closely packed structure, the molecules and the molecular structures are arranged in a very confined manner, so that energy and other way energy stored molecules are significantly arranged in a granular form. So granules are a part of our heritage, especially with respect when we explain with respect to hunger and food supply and food sufficiency. Then farming and cultivation of crops are done for the hunger god. You know, hunger is regarded as the greatest god for the ecosystems, especially animal kingdom. Then for cultivation and for harvesting grains, we need soil. What is soil? Soil is a natural porous material. It absorbs and hold on and release nutrients from aqueous and liquid interface. From the introductory part, I have mentioned that the significance of soil structures, the significant behavior of soil as a ideal medium to hold on nutrients and water, and the medium for agricultural practice. The soil enrichment improves the yield of the crop yield and the nutrient capacity of the soil. So the prosperity of a nation, a prosperity of a country, the prosperity of entire the globe is decided by the textural characteristics of the natural soil. So soil is natural porous material. It absorbs and hold on and release nutrients from aqueous liquid interface. Engineers will interpret the meaning of the mass transfer phenomena, as well as interface mass transfer. Everything ultimately leads to the concentration, the phenomena where the molecules and ions are get concentrated between the phases. Soil allows the vertical movement of water molecules by capillary condensation. I have mentioned about the fundamental behavior of soil structure. Soil has property of porosity and surface area. Then pore filling mechanism is involved when soil is in contact with the liquid water. This is some philosophical or holistic approach related to porous material, and we are very familiar with soil. That is the most well-known and well-explained porous material in nature. Then comes to the significance of soil with respect to its capacity to hold on materials. that is come in contact with its own natural course of movement. We are taking 1 gram of soil, it can hold 1 gram of soil means, suppose 1 gram of soil is holding 1 mole of water. This is a basic elementary chemistry, and I have mentioned that you were directed to your past memories you cherished when you were at the age of 16 or 17, the concept of mole and molecular weight, especially particularly for Boyd's law and Charles' law, studied for your +2 days. That is 1 gram of soil. We are assuming that 1 gram of soil is holding 1 mole of water. That means it can hold on 18 gram of water. 1 mole of water means 18 gram of water. That is H2O. That is 2 grams of hydrogen, 2 grams, and 16 gram of oxygen. That is 18 gram of water. Under STP conditions, ideal gas equations, and fundamental laws of chemistry, 18 gram of water at STP can occupies 22,414 cubic meters. That means 22.414 cubic meters. Otherwise, 22,440 cubic meters. That is 1 mole is equal to 1 mole of material can have a volume 22,414 cubic centimeter. The concept of Avogadro's number, mole, the concept of mole is here, the concept of STP volume, ideal gas condition is here. Then the concept of Avogadro's number, Avogadro stated that 1 mole of a substance contains 1 Avogadro's number of molecules. That is 1 mole of a substance. In the case of water, it is 18 gram of water is taken. If you count 18 grams of water in molecular wise, you are counting the number of molecules maintained in 18 gram of water is consisting 18 gram of water. You will get a total number of water molecules equal to 6.023 into 10 raised to 23 molecules of water. The cross-sectional area of water is, when a water is placed on a table, on a surface, it can occupy an area in terms of nanometer. It is a they are atomic particles. Atoms are having subatomic dimensions, that is in nanometer scale, the dimensions are expressed. That is, the cross-sectional area of water is 1.40 nanometer square. This is the cross-sectional area of one water. If you place 1 molecule of H2O in front of you, then the total area occupied by 1 molecule of water, not 1 mole of water. 1 molecule of water is equal to 1.40 nanometer square. That is 1 mole of water. Then we can have a final formulation that 1 mole of water is equal to 18 gram of water. 1 mole of water means 18 gram of water. 1 mole of water contains 6.023 into 10 raised to 23 molecules. If one molecule is having a cross-sectional area of 1.40 nanometer square, that is cross-sectional area. Instead, here I have taken as A. A is the cross-sectional area of water. So 1 molecule is having 1.40 nanometer square. Therefore, what is the total area for 6.023 into 10 raised to 23 molecules? That means it is equal to 6.023 into 10 raised to 23 multiplied by A nanometer square. A is the cross-sectional area of water in the case of water. Nanometer square can be converted to meter square. 1 nanometer is equal to 10 raised to minus 9 meter. So nanometer square is equal to 10 raised to minus 18 meter square. So we can say that 1 mole of water, if you are considering, it has 18 gram mass. That means it has a surface area of 6.023 into 10 raised to 23 multiplied by the cross-sectional area of 1 molecule multiplied by nanometer square multiplied by 10 raised to minus 18 meter square, so that the nanometer can be ultimately made to meter square. In engineering calculations, surface area is measured and expressed in terms of meter square. Therefore, the cross-sectional area nanometer square is converted to meter square. Suppose a gram of water is taken instead of 18 gram. Here 1 mole instead of 18 gram, I have taken a gram of water has taken, and it is get absorbed in 1 gram of soil. Then what is the total surface area contributed by a gram of water on a gram of water absorbed or accumulated or concentrated on 1 gram of soil? The calculation is like that. If 18 grams of water is having surface area equal to that much, what will be for a gram? You know, this is simple calculation. For 18 grams, the surface area is this much. That is 6.023 into 10 raised to 23. Cross section multiplied by cross sectional area A. Instead here area cross section area is equal to 1.40 nanometer square multiplied by 10 raised to minus 18 nanosphere. This is if it is for 18 gram. What will be the volume, the surface area for a gram? So multiply this factor with A. So this is the surface
me,
area
sir.
of. Hello.
May I just ask a clarification, sir, please?
Yes.
Sir, in this a gram of water has a surface area equal to A into 6.023 into 10 raised to 23 into 1.4 multiplied by 10 raised to minus 18. After that, it is meter square only, right, sir?
It is meter square only because here
It is,
I have to change. This is here, that is 10 raised to minus 18 meter square. This n accidentally happened, and you have to remove that n because here once multiplied by 10 raised to minus 18 meter square, this is meter square. Ultimately, it is meter square because surface area is reported in terms of meter square.
Please proceed.
So minus 18 comes, then it comes meter square. It is 18 gram. So this calculation is very, very, very important. That is the basic understanding of the chemistry. This moles, molecular mass, STP volume, Avogadro's number relationship is most confusing for the entire scientists in the world who are working in the field of chemistry, physics, biology, or engineering. If this relationship, what is meant by mole, what is meant by the molecular weight, how it is related to Avogadro's number, this is the basic equation for all calculations in chemistry as well as in physics. That is 1 mole of substance occupies 1 molecular weight of the material that contains 1 Avogadro's number of the molecules that has a total volume of STP volume of 22,414 cubic meter. This is the foundation of analytical science, analytical chemistry. This is the foundation of entire scientific innovations occurring in the world. Beyond this equation, nothing can be done, nothing can be perceived. This equation is beautifully adopted by Brunner and Emmett for their calculation of the surface area. Then a gram of material is having the surface area that much of square meters. You know, each and every material, if you take any material and it is quantity is measured in weight, you can translate into volume because 18 gram, 1 molecular weight of any substance occupies an STP volume, equivalency of STP volume of 22,414 cubic meter. Any method where weight is measured for quantification, that method is known as gravimetric method because chemical engineers and those studied chemistry at elementary level, gravimetry means a measuring technique where weight is particularly concentrated for the quantification. You know, weight can be converted to volume by the simple calculation converting to STP volume. You know, here we can say that if 18 gram of water can occupy STP volume of 22,400 cubic meter, what will be the volume? Instead of a gram of water, I am taking V ml of water because a gram of water can have a volume of V ml. Then what will be the surface area? Instead a gram, if a gram is having a volume of V ml, V cubic meter, then V ml of water occupy a surface area equal to here molecular mass or molecular mass in terms of mass of 1 mole of substance, where 18 is changed as 22,414 cubic meters. And instead of A, equivalent volume is multiplied. Cubic meter, here cubic meter. No variation in the calculation. Here the volume, the surface area is again the same surface area can be obtained when it is converted into the equivalency of volume. The same quantity of the surface area can be calculated, because there are two analytical methods where surface area can be measured. First one is the gravimetric method. The second one is volumetric method. The micrometrics instrument, most of the instruments we have nowadays, the two methods can be used, but particularly the volume-based calculations are adopted. The interchanging is possible because only the multiplication with the molecular mass is possible. So this is the basic equation for the determination of surface area for simple chemical arithmetic calculation. Here the problem is that how this volume absorbed by 1 gram of the mass can be determined. For that purpose only we are using an analyzer. The usage of an analyzer is how much volume of any gas is absorbed, or how many grams of any substance is absorbed by 1 gram of a solid porous material. For that determinations we use analyzer, that is surface area and porosity analyzer is used. This is the basic calculation. Again, I will take into the calculation VML of nitrogen gas. You know, I have mentioned that nitrogen is the common gas available. It can be easily liquefiable. It can be maintained at a temperature of minus 196 degrees centigrade. Brunner and Emmett and Teller utilize nitrogen because it is non-polar gas. No dipolarity is there, just like carbon dioxide or water. So liquid nitrogen, they applied at a very low temperature, 77 K, to fill on the surface of 1 gram of any material required for the testing, and they calculated the amount of the volume of nitrogen absorbed by 1 gram of the substance. The V can be calculated from the normal isotherm plot, and put into the calculations, we can calculate the surface area of material. So nitrogen as a probe molecule is widely accepted as a method to determine the surface area. In BET analysis also, liquid nitrogen at 77 K is used as a probe for filling the porous structure and surface area of any porous materials, and the volume absorbed by unit mass of the porous material is taken as V, and it is put into the calculation, and ultimately the surface area is calculated. Here again, that is meter square, nanometer is a mistake. I have to change it. Finally, here, 0.162 in the case of nitrogen, the cross-sectional area is 0.162 nanometer or 16.2 Armstrong square. Calculation between nanometer, between angstrom, between meter is very, very significant in this in this practice of calculation. So what is nanometer, what is angstrom unit, and what is meter? Here again, when we are using the nitrogen, the surface area calculation is V, the volume absorbed has to be taken from the instrument, or when you are given with a problem, the volume absorbed by unit gram of the material has to be given in the problem, and the cross-sectional area must be known. What type of probe is utilized, then calculations can be made. In the case of nitrogen, the cross-sectional area is 0.162. So please note down these calculations. I will give you some questions because it is a faculty development program. I will give you some simple calculations. You calculate and report the result. So write down these equations. If everything is noted, I will give you some calculations. Are you ready? Hello? Nishida?
Yes,
Hello?
sir.
Am I audible?
Yes, you are audible, sir.
So anybody wants to do some problems and calculations?
Participants?
Participants, please. I will give you some problems.
Please.
Yes.
Hello? Hello?
Hello, sir. Participants are interested.
Interested.
Yes, sir.
See, dear students, usually nitrogen is used. What is the cross-sectional area of nitrogen molecule? Give me the answer. What is the cross-sectional area of a nitrogen molecule?
It is 16.2 angstrom, sir.
Angstrom or 0.162 nanometer square. Okay.
Okay, sir.
Then another molecule utilized in surface area analysis, carbon dioxide. You know, carbon dioxide is applied at 0 degree centigrade. Nitrogen at 77 K. If you are using carbon dioxide, the isotherm is plotted at 0 degree centigrade. For carbon dioxide, the cross-sectional area is 0.172 nanometer square. 0.170 nanometer square. If there are finer pores, if it is nanoporous material, because nitrogen cannot go very deep into very finer pores because the size of nitrogen is huge. Its size is 0.162. In that case, argon is used or hydrogen can be utilized. In most cases, argon is used. For the argon gas, the cross-sectional area is equal to 0.138 nanometer square. So depending upon the nature of material, we can't measure the porosity of every material using nitrogen. If some materials, the pores will be large, so the nitrogen can be percolated, can occupy. In other materials, if the pores are very small, you can go for hydrogen gas, because hydrogen gas, the size is very small, it can diffuse into the finer pores. In some cases, carbon dioxide can be utilized because nitrogen has some steric hindrance with the surface functional groups of the material. In that case, we can use carbon dioxide. Then I will give you a problem. Please note it down. A clay material. Hello? Hello? A clay
Yes, sir.
material is analyzed in a BT analyzer. Is analyzed in a BT analyzer, and it is found that 1 gram of clay, 1 gram of clay absorbed 100 cubic meter of 100 cubic meter of N2 gas, nitrogen gas, N2 gas at 77 K. N2 gas, nitrogen gas at 77 K. The cross-sectional area of one N2 molecule is, the cross-sectional area of one N2 molecule is 0.162 nanometer square. 0.162 nanometer square. What will be its surface area? What will be the specific surface area of the clay material? What will be the specific surface area of the clay material? What will be the specific surface area of the clay material? You know, the porous material is clay. 1 gram of clay absorb 100 cubic meter of nitrogen. Cross section of nitrogen is given. The temperature is given. You are asked to calculate the surface area, specific surface area. Specific surface area means the surface area per unit gram of the material. That is specific surface area. Here I have mentioned that 1 gram of material is taken. That means that is a specific surface area. What is the surface area per unit gram of the material is known as specific surface area. Usually surface area is measured and expressed in terms of specific surface area. Please calculate and report me the surface area you obtained. There is no complexity is there. You put the values in the equation, the same equation that is projected here, and report the result. That is all. It is done. You got the answer? Here you can see that is 6.023 into 10 raised to 23 multiplied by 0.162 into 10 raised to minus 18. You know, 23 and 18 cancelled. Ultimately, final equation is 10 raised to 5 meter square. Sorry, 10 raised to 5 and multiply 30. Got the answer? Hello? Hello?
Sir, is it 435.32?
That is 435.31. 435.31. What is your name, please?
Myself is Rishmi, sir.
Sorry?
My name is Rishmi, sir.
Rashmi, you are from which
I
institution?
am from NSS Engineering College, sir, Palakkad.
Oh, Rashmi, congratulations. You learned something.
It's very interesting, sir. The first time
Yeah,
I am
yeah.
listening to such a nice talk.
What is your background? Chemistry or physics or engineering?
Environmental engineering, sir. I did works related to this area only, sir.
Okay, environmental engineering for MTech or BTech?
Sir, I did completed PhD also, but I am listening to such a talk for the first time. Very nice session.
Thank you. You completed in BTech in which subject?
Civil engineering, sir.
Okay. Because now you became very, very strong in your +1 class. Going back to the field is a practice by those agricultural scientists, just like we are going back to our higher secondary classes. Now you are familiar with what is mole, what is Avogadro's number, what is STP volume, and
Sir.
how it is related to the entire computation of the universe. Clear?
Very nice, sir. Thank you.
Then another problem, you see, Rashmi, then I will ask you for the support. Suppose I am giving you the cross-sectional area as 16.2 angstrom square, then how will you calculate? Here the cross-sectional area of nitrogen is given us in nanometers, 0.162 nanometer square. Instead, I am giving you the cross-sectional area of nitrogen as 16.2 angstrom square. Then how will you proceed with the calculations?
No change required, sir.
No change required because, you know, 16.2
It's same
angstrom
as
square is equal to
0.1.
0.162 nanometer square. Okay.
Okay, sir.
Then another question. Simple question. You don't worry. The equation is here. Only what we need is a logical thinking. Our interest, our brain has to be so much happy with the calculations. That is the most important thing. Just like seeing a serial or listening to a film song, you have some interest in your mind with these calculations. Again, the question is like that. 1 gram of iron oxide catalyst, you know, engineering people working in plants, process, tubular reactor performance, fed batch reactor operations, CSTR constantly mixed tank reactor operations, and everywhere catalyst is generally used. Of course, oxides of nitrogen are the general category of catalyst used in various applications. Here come to the calculation of such a problem. 1 gram of iron oxide catalyst used in a refinery operation. 1 gram of iron oxide catalyst used in a refinery operation. Absorb 100 cubic meter of carbon dioxide. 100 cubic meter of carbon dioxide. Gas, 100 cubic meter of carbon dioxide gas, when it is analyzed, when the material is analyzed in a BET surface area analyzer, when it is analyzed in a BET surface area analyzer, at 273 K, at 273 K, at 273 K, the cross-sectional area of a carbon dioxide molecule, CO2 molecule, the cross-sectional area of a CO2 molecule is 0.170 nanometer square. 0.170 nanometer square. The cross-sectional area of one CO2 molecule is 0.170 nanometer square is nanometer square. Question the cross-section area. Determine the specific surface area of the catalyst. Determine the specific surface area of the catalyst. The same question, instead of nitrogen, we are applying carbon dioxide. Carbon dioxide is applied at 0 degrees centigrade. That means 273 Kelvin. The cross-sectional area will be changed in the final equation. Instead of nitrogen, we are substituting 0.170. You substitute the cross-sectional area carbon dioxide, that is all. Answer?
Sir, is it 456.82?
Answer parayamo? Hello?
So what it is 456.82.
4 56.8 square meter per gram. This answer is correct. Rashmi thaneyano report cheythathu vera arilum ano?
Yes, sir.
Anybody else there? You are attending in the classroom or online? Are you attending online or in the classroom session? Hello, Rashmi.
Sir, please.
Are you in online or you are attending the lecture session physically in the classroom?
In online only, sir.
Online only. So you cannot support the others. Okay. You can explain. How will you? Can you explain the calculation in your own words?
Sir.
What are the benefit of others, other participants?
Here 100 meter cubed carbon dioxide gas is given. So 100 into 6.023 into 10 raised to 23 is Avogadro number. That into it's for carbon dioxide surface area given is 0.17 multiplied by 10 raised to minus 18. That divided by 22,414. So the calculation becomes 6.023 into 10 raised to 25 into 0.17 into 10 raised to minus 18 divided by 22,414. So we need to cancel 10 raised to 25 into 10 raised to minus 18 so that the calculation become easy. Then we can directly get the answer.
Okay, thank you. So Nishida,
Okay,
hello.
Yes, sir.
അവിടെ ഇരിക്കുന്നവർക്ക് ഇത് മനസ്സിലാകുന്നുണ്ടോ കാൽക്കുലേഷൻ?
Sir, pardon, sir?
അവിടെ അറ്റൻഡ് ചെയ്യുന്നവർക്ക് ഇത് മനസ്സിലാകുന്നുണ്ടോ കാൽക്കുലേഷൻസ് ഒക്കെ?
Yes, sir.
Okay.
All are doing well.
Yeah, that is fine. But is you have learned something regarding the basic calculation of the surface area. Let us proceed to the next slide. You know, this is the way the molecules are packed in the pores. You know, I have mentioned a catalyst or clay and a iron catalyst. When it is placed into a sample tube and nitrogen gas is allowed to pass through that, you know, nitrogen molecules, here you can see that nitrogen molecules are just like spheres getting accumulated. First, a simple one layer formations are done. This is the beauty of Brunner-Emmett equation, that is the volume absorbed by 1 gram of material to complete the first layer of molecules. You know, the molecule never randomly arranged in a surface. Molecules, just like how we stand for Q. In a particular occasions, the molecule will be standing Q to occupy their chair, one after another, so that the entire surface is initially filled by one layer of molecules. You see, 1 gram of the molecules, the entire surface is uniformly occupied by a single layer of molecules. You know, this will be equal to 1 Avogadro's number of molecule. In the case of 1 molecular weight of the substance is taken. If 18 grams of water is taken on the surface of 1 gram of the material, 6.02 into 23, 10 raised to 23 numbers of the molecules will arrange one after another to the entire bulk surface area of 1 gram of the material. This is known as the completion of the monolayer. Once the completion of monolayer is detected in the graphical representation of the Brunner isotherm plot, then we can get the monolayer coverage. That monolayer coverage is very, very important for the determination of surface area. In the equation, this V is equal to monolayer coverage. That is in the Brunner-Emmett equation, they have mentioned VM instead. You know, VM is applied. VM is the monolayer coverage. That is the monolayer coverage. The equation, you can see the monolayer coverage. That is the VM. Yeah, slide on question. Wait ചെയ്തിട്ട് സ്ലൈഡ് വരുന്ന പ്രോബ്ലം അവർക്ക് കാണാം. ഓക്കെ, പാർലറ്റ് സ്ലൈഡ് സ്ലൈഡ് വരുമ്പോൾ എനിക്ക് തോന്നുന്നത് വീഡിയോ വന്നതിന്റെ പ്രോബ്ലം ഉണ്ട്. എടുത്ത് കളയാം. പിന്നെ ഇവിടെ ഇന്നും പ്രോബ്ലം. കഴിഞ്ഞിട്ട് ഇവിടെ വന്നാൽ sorry again, some problem because I have incorporated a video in the slide. Once moving through that slide, it start to hang. We have to remove that video. This is the monolayer coverage. You know, here it is okay. Nishida, hello. Hello. Okay.
Yes, sir. It's clear.
When the molecules are accumulated on the surface, the first layer is completed. Then only the second layer start. That is the adsorbate in the first layer. It is known as the monolayer coverage. Once the uniformly the molecules are arranged in the entire surface of 1 gram of the material, the second layer start to accumulate. That is the formation of the multi-layer. That is the pore filling. The entire pore is getting filled, but initially only the side is filled with one layer of the molecule. Then unadsorbed molecule will accumulate, because the adsorption occurs in different phases. First one is the monolayer adsorption. Second layer is the multi-layer adsorption. Then third layer is the capillary condensation. That is, there are 4 different stages for adsorption: monolayer adsorption, multi-layer adsorption, then followed by capillary condensation, and the fourth one is free liquid. Here the molecule will be compressed, and the gaseous molecule will be compressed, and they will exist as a free liquid. You know, the Stephen Bruner, American researcher, chemist, government scientist, and university teacher, American chemist. He was a classmate of Linus Pauling. MIT has been the classmate of Nobel laureate Linus Pauling, and even Einstein several times approached Stephen Bruner for getting job in some of the government department. The letters are very prominent. And the Edward Teller, later he becomes an architect for the atomic bomb and hydrogen bomb, because their contribution based upon this porous nature of the materials, even the explosive materials, their high energy content is mainly because of the porosity and surface area. So their contribution in the modern science is enormous. In 1938, they published the first article on BET theory. This paper article is the basis for the surface area analysis and the instrumentation. This is the first paper published by Bruner and Emmett and Teller in American Chemical Society in 1938. Even nowadays, you know, after near to 100 years, this technique and instrumentation method is very valid. This is the equation, this is the paper published, and this is the textbook published by Bruner. And they worked together only 4 years, and later the group is dispersed and they went for different jobs. And after 40 years, they joined together only in 1965 for receiving their honorary PhD degree. You know, 3 people coming from 3 different areas working together in a fertilizer quality control laboratory. They have done huge contribution in science. The first person is a physicist, second person is a mathematician, the third person is a chemist. They contributed much. They work only for 4 years. They never done any PhD research work. They only got a honorary PhD degree after many years. Then when the industry, the lab identified that fertilizer industry is not economically viable, their job is lost. This is the life history of Bruner and Emmett. Then this is the essence of this BT analyzer technique. Gaseous molecules behave ideally, that is ideal gasification is valid. Then gas adsorb on a flat uniform surface of the solid with uniform heat of adsorption. and they accumulate in different layers due to van der Waals forces. Multiple nitrogen molecules can be observed in each site. You have seen that, how the layers, the pores are filled as layers. Now all sites on the surface are equivalent. That is, just like the people are occupying the chairs, the molecules are occupying their respective positions to confirm the monolayer in a porous surface. No adsorbate interactions. There is no chemical interaction, no bond making process, bond breaking process occurring during fission of the gases. An adsorbate molecule is immobile. Once it is adsorbed, it never moves. It is stationarily bound in the position. Nitrogen in the second layer and higher layers are assumed to behave like liquid. Adsorption in the second and subsequent layers occurs with a heat of adsorption equal to the heat of liquefaction of gases. When the molecules behave the same property and behavior is everywhere, the material behave. Then in metallurgical operations, material science, in civil engineering operations, whatever the molecules in elementary level behaves, that phenomena and significant observations can be applied in your future scientific encounters. So these concepts are very, very important. As the microcosm, so is the macrocosm. How the molecules behaves in molecular level, that is the behavior of the entire universe. This is the significance of material science, especially the interaction of the molecules with bulk material in a microscopic level. Now, here we can have the adsorption of isolated molecules. Here the monolayer coverage graphically is represented by micromeritics in their technical report. And here the multi-layer filling, condensation, I have mentioned the capillary condensation. So when the molecules are percolated, water molecules are percolated through a soil matrix, these van der Waals forces are utilized for movement of the water molecules in soil horizons. So the agriculture and other practices are only possible due to the percolation of the water molecules on the surface of the porous soil structures. This phenomena is applied in a wide perspective. Here, the basic principles of Gay-Lussac's law is applied. When a pressure is increased, the temperature is increased. When pressure is increased, the volume of the gas gets adsorbed on the pore volume is decreased. Very high pressure, low volume is, the volume is reduced and the volume is accumulated. Low volume means the molecules are confined on the porous structures. So the Boyle's law, Charles' law, and Avogadro's law, and Gay-Lussac's law studied in our +1 days are significantly discussed, and it becomes a very, very important analytical tool in the material science and engineering. This is the significance of surface area determinations. Here, how the Boyle's law, Charles' law, and Avogadro's hypothesis are applied. When a gas is allowed to accumulate on the surface of a porous material, again, the theory is explained. What is an adsorption isotherm? The monolayer gas adsorption, multi-layer gas adsorption in a different way. This is significantly interpreted by Brunner and Emmett. The concept of accumulation or concentrating molecules on another phase first perceived by Irving Langmuir, and he formulated a theory, that is Langmuir adsorption isotherm, that was in the year 1906. And Langmuir was a disciple of very, very renowned scientist, that is Walter Nernst. Nernst equation, Nernst equation in electron chemistry and the electrical energy concept, and the contribution of the electrons, and how the chemical potential of the materials can be harvested in the form of electrical energy, and everything is by Nernst, and he was a disciple of Nernst. A good heritage is followed from Jane to Jane, that ultimately happened in the science of materials, especially the physicization of the materials and analytical determination of the porous material. Then this is some of the pictures. Langmuir is contributing how the pressure volume relationship ultimately can be utilized for measuring the adsorption efficiency of the porous materials. And Brunner and Emmett modified the Langmuir equation And the formation of monolayer is the concept of Langmuir, and Brunner and Emmett mentioned that the completion of the monolayer is very significant, and adsorption occurs beyond the monolayer. So the concept of monolayer and multilayer adsorption phenomena is introduced by Brunner and Emmett. This is Langmuir equation. Here again, when the pressure volume curves are constructed, again a straight line relationship is obtained. From the slope and intercept, we can determine the surface area and porosity of the material. I have mentioned that what are micropore material and mesopore material and macropore material. Depending upon the pore size, the material classification is given. I know that the time is running out. I hope within 5 minutes I can finish, because some time lag happened during the presentation. Then adsorption phenomena, monolayer adsorption, multilayer adsorption, and capillary condensation. This is BET theory to explain the physical adsorption of gas molecules into the solid surface. Again, you can imagine how the molecular interaction occurs in the three-dimensional space. The particle size, when the particles are grind, then the edges are enhanced. If there are more edges, more surface area. So porous materials, if the size is small, geometrical size is small, their surface area is huge. The surface area can be improved. Then adsorption and adsorbent interaction. Adsorption can be interpreted in two ways: physisorption and chemisorption. Physisorption and how the BET theory extends to Langmuir theory, and ideal solid surface, actual solid surface, how the layers are built upon one after another one. It is again graphically expressed. This is BET isotherm equation. Here the monolayer, once the data is plotted, yes, we can get a straight line. You can take the slope and intercept. 1 by the sum of slope and intercept will give you you take the volume adsorbed. This is BET equation. The first one, that is Y value, is plotted again in the graph Y versus P by P0. This equation is, here is the intercept. This is the slope. This is the intercept. The slope, it contains the monolayer volume Vm. Once Vm is obtained, put into our initial equation. The equation we practiced several times. Here the volume adsorbed by 1 gram of the material is very important. That volume folded by 1 gram of the material for the completion of one monolayer, one layer of the molecules, that is Vm, because we are using the instrument for determining the Vm value. For once Vm is obtained, put the value of Vm in the equation and obtain the result. That is, Vm is obtained. From the Vm, we can calculate the surface area, because the total surface area is equal to Vm multiplied by the same equation we practiced. The surface area of the material, the total surface area of the material. If it is divided by the total weight of the material, you will get the specific surface area. If you taking X gram, the total surface area is known as ST. If you are taking 1 gram or divide by the total weight, then you will get specific surface area, that is SBT can be obtained. That is SBT is equal to, or the surface area is equal to monolayer volume adsorbed. That is, I have given in through 2 problems. The volume adsorbed per unit mass of the material is Vm multiplied by Avogadro's number. S is the cross-sectional area in nanometer. Depending upon the probe molecule used, the S value changed. Then Avogadro's number is here. Then conversion to nanometer into meter is your logical calculations and manipulations, how the nanometer can be converted to meter square, that I have mentioned in the calculation. Then the surface area can be determined, microporous material, mesoporous material, and macroporous material. Mesoporous material, silica, activated carbon, and they belongs to mesoporous material. Zeolite, then granular activated carbon, metal organic framework, they are microporous in nature. And macroporous material, sintered metals and ceramics, they are macroporous material. The size reduction and the material characterization, everything is given. When a material is, if you analyze the entire material is available in the world, in a BET analyzer, different shapes of the graphs are obtained. If the first graph, if the material will provide you a graph of this unique shape, we can say the material belongs to type 1 isotope. If the material is giving the shape of the graph, this, then you say, IUPAC technical report say that that is a porous material of the type 2. If the graph, the normal isotope is this shape, the material behaves just like a type 3 material. If a mesoporous material is utilized, the shape, the most of the mesoporous material will give you the isotope shape equal to this one, which is a type 4 material, then type 5 material, then type 6 material. Then whatever the material available in the entire universe, analyze it in a surface area analyze, it will belongs to any of these categories. This is something regarding the small surface area and the large surface area materials. And this is regarding the entire classification of the porous materials. I hope that we have come to the calculation of the Brunner-Emmett-Teller equation, the basic hypothesis of adsorption. Then what is a porous material, how the porosity is determined, how the water-soil interface behaves, what is an isotope, what is a normal isotope, how the data are generated, and the surface area is calculated. Then the IUPAC technical report, this paper is available. You take a picture of this technical report and have a copy of the technical report whenever you are studying on a material in a project or any student project. Writing something based upon the technical report is very, very important. Then calculations, then monolayer adsorption, how the multilayer adsorption occurs, something regarding the distinguished scientist Brunner and their first publications, assumptions of multilayer monolayer adsorption, how the pore filling occurs, then the fundamental rules, the laws of chemical combinations for perceiving surface area determinations, isotopes, again surface phenomena, something regarding Langmuir isotope models, then basic concept of monolayer, then classification of materials according to the porosity, then something regarding how the geometrical size of the material determines the surface area, and calculations of the Brunner-Emmett equations and monolayer adsorption, the graphical simulation, how the slope can be obtained, and further calculation of the surface area. And I hope we have learned something regarding this subject.